Welcome everyone, and thank you for joining us. I'm Brenda Dettinger from BioPack, and I will be your moderator on today's webinar. We're going to demonstrate autonomic function testing, including Valsalva maneuver, deep breathing, and active standing. This is going to be a very action-packed webinar. We have some theory, we have some analysis we're going to share with you, and so stick around. It's going to be a full webinar, but very cool and very interesting to watch. So first, before we dive in, I have some housekeeping. All attendees are muted, so please submit your questions and comments through the GoToWebinar control panel. That's how you communicate with me, your moderator. We also have Colt Bush in the background helping answer questions, and he can help with any technical problems that you have as well. Hopefully we won't have any, but that does happen during webinars. When the webcam is turned on, if it looks small to you, you can resize your window by grabbing this little gray bar right here and enlarge or shrink back down. Today's webinar is being recorded, and we'll send each of you a link to the recording once it's done processed. Usually that's like in 24 hours. And finally, we'll have a survey at the end of the webinar. Please complete it so we have your feedback and ideas. Now on to our presenters. I'm really excited to introduce our experts today. We have a special treat. We have Dr. Sanjay Sood. He has his PhD from All India Institute of Medical Sciences, New Delhi. He has over 32 years experience working with a diverse medical student population as a physiology teacher and a researcher. He's currently a consultant with BioPack. Welcome, Sanjay.
Hi.
Also, we have Alex Dimoff. He's a BioPack product expert and has taught over actually close to 150 workshops now on the topic of physiological data acquisition and analysis. He's been with BioPack for over 15 years. Welcome, Alex.
Thanks. Welcome for joining us.
All right, let's start with Sanjay. I'm going to make you presenter. Here you go. Looks great.
Hi everyone, welcome to the webinar. Before we start, I would be sharing some information about BioPack. You see, BioPack develops state-of-the-art technology so that you can record various physiological parameters anytime, anywhere, in any subjects. We have been in this business for the last 30 years, and 99% of the top universities across the world use BioPack system. And till today morning, BioPack has been cited around 45,000 times. So let's come to the webinar topic. So today, we are going to discuss autonomic function testing. We have divided it into two series. So today, we'll be primarily focusing on deep breathing test, or Valsalva maneuver, and lying to standing. You all would agree with me that starting a research is a very tedious job. So one needs to find out the hypothesis or the basic idea. But with the advent of newer technology, there is another dimension which has been added. So the complexities of equipment uses, analysis is a big issue. So when we were planning this webinar, this is what we had in our minds. So we thought that we'll divide this webinar into two components and we'll highlight the basic concepts. So by the end of the webinar, you'll be able to understand the basis of autonomic function testing. You'll be able to list various requirements if you're planning to set up a new lab. And of course, we'll go step by step. We'll be demonstrating all these tests, Valsalva maneuver, deep breathing test, active standing for today's webinar. And in the end, you should be able to recall all the demonstrated concept. And of course, in the end, I'll be just give you an overview of the recent advances. You know, because the limitation of time, it will be impossible to cover all the domains. You see, when you set up a new lab, there will be some attendees who must be planning to set up a new lab. So you have to keep few things in mind. Lab space is very important because especially when you do autonomic function testing, So what you need is a lot of equipments. Then you need, chairs, lying down chairs. And then, of course, in addition, you need technicians, supervisors. So generally, it's recommended that around 250 square feet is more than enough. Then, of course, the next important factor is that the lab should be situated in a quiet place, because disturbance noise can alter cardiovascular function. So you have to choose that area. Then the next important factor is that the lab should be operated within an ambient temperature, 23 to 25 degrees centigrade. And the reason being that if the temperature is not in the thermoneutral zone, so there will be peripheral vasodilatation or constriction depending on the temperature, which will alter the cardiovascular responses. And similarly, the humidity also should be maintained between 25 to 35%. And of course, we need 2 trained technicians and 1 supervisor who should be certified. The role of supervisor is also important while doing lying to standing and also head up tilt, because in case of any emergency, the supervisor will be able to manage the emergency. Plus, as I discussed, the analysis part is a little complex. So if there is any certified experienced supervisor, that will be of great help. Of course, the last one is equipments. You see, these days research is also technology based. So there are many options. So let me share with you what we have at BioPack. We have a platform which is applicable to more than 40 research fields, from cardiovascular to neurophysiology to virtual reality, neuromarketing. Now, let's talk about some focused equipment which you may need for this autonomic function testing. The hub is a MP160 system. It is a modular system which acquires and records and analyzes the signals. So here we have a MP160 system. It is also having attached module which can record 60 channels. In addition, we have these days what you call smart amplifiers. They are very close to the subject, so the signal they produce is really very faithful. Then the other option is wireless. So we have bionomadics, as the name suggests. Nomad means anywhere, anytime. You can log in, and this can also be, there can be another attachment which is known as logger. So a person can go around outside the lab, so we can record for 24-hour battery life is there, so we can record for longer time. 6 channels. There are also scope for inputs like auditory inputs, stimulus markers. So it's really very versatile tool, and especially for recording cardiovascular parameters. Then another one is universal amplifier, 4 channels, which can be used for teaching also. So this is a good choice for those who just want to do simple research and also want to use it for teaching. So this one has many other options. It can give sound output, it can give electrical output. The outside stimulus can be synchronized by digital or BNC input. So this is really very, very versatile equipment for beginners. Then another thing these days is, as the technology has advanced, we have the option for using beat-to-beat measurement of blood pressure. So this is NIBP 100E, which is a CNAP technology, that is continuous non-invasive arterial blood pressure measurement. And here what is done is the vascular unloading is done, and then it's picked up by the gadget. So it's really very valid and specific and sensitive tool which is employed these days. Just to emphasize further, most of the equipments we sell are MRI compatible. Now, as I started in the beginning, that recording autonomic function testing is a very tedious and time-consuming job. So one has to be really very precise, and one needs to have a lot of experience so that the results are reproducible. So For that, one of the most important thing is instructions to the subject. The subject preparation is very important because if it's not done properly, it may alter your results. So caffeine and nicotine should be completely stopped 4 hours before the test. Alcohol, no consumption after 8 hours. Medications, 24 to 48 hours, one has to stop. And these recommendations are very practical because in case of clinical setting, there are some patients who are taking very, very important medicines. So stopping them for more than 2 days is not justifiable. Then, of course, food intake. The subject can take very light food up to 2 hours, not after that. So he should avoid heavy meals prior to the previous night also. Another thing is the subject or the patient should avoid heavy exercise 24 hours before going for the test. And the subject should do these tests with the bladder empty. And of course, the last one is time of the day is very important. Suppose if you are repeating the test, and in a clinical setting, sometime for prognosis, you also repeat the test. So it's better to fix up a time and repeat at that point of time so that the circadian rhythmicity is taken care of. So this is in brief about preparation of the subjects. Now let's come on to the autonomic function testing. You see, human body is like a system which is regulated by various negative feedback control systems. And the various visceral functions are regulated by autonomic functions, autonomic system. For example, our blood pressure, heart rate, body temperature, digestion, fluid electrolyte balance, sweating, urination, defecation, all controlled by autonomic system. Now, out of all these, it's only the parasympathetic and sympathetic nervous system which is quantifiable because we can measure heart rate, blood pressure. So there is a small window for opportunity to peep into the system and find out what is the status of autonomic nervous system. Of course, we also have some measurements about some other aspects like sympathetic cholinergic system by doing sweat tests, sympathetic adrenergic system by measuring plasma adrenergic levels, and enteric nervous system is still it's in its infancy, but by doing EGG electrogastrography you have some idea about the status. Now let's come on to the sympathetic and parasympathetic nervous system. Generally, there is a concept that they both are antagonistic, but that's not the case. Both sympathetic and parasympathetic nervous system, they work in unison. They complement each other. It's like you can say that sympathetic nervous system is like an accelerator, whereas parasympathetic is like a brake. So they both work together to achieve a homeostatic control for any given variable. Now, as I discussed with you that we today will be discussing primarily measuring sympathetic and parasympathetic nervous system. So the parasympathetic nervous system basically can be measured by measuring deep breathing, Valsalva ratio, and lying to standing, active standing. So this is known as cardiovagal innervation test. The sympathetic one is cardiovascular adrenergic system can be measured by recording beat to beat blood pressure. So this can be measured during Valsalva, sustained hand grip, and lying to standing or head up tilt. And of course, the sweating test can also be done, which gives you some idea about global or local neuropathies, autonomic neuropathies. So I'll be touching briefly in the end about QSART and TST. Let's come on to the autonomic function testing. That what is the basis of this? You see, most of the physiological function in the body have a set point. For example, blood pressure. So we have a normal range of blood pressure. So the body has a cardiovascular regulatory mechanism which keep this blood pressure maintained at that set point. Let's say it's 120 by 80 millimeter of mercury. So whenever there is disturbance to these variables, maybe there is blood loss, or maybe there is increase in blood pressure, or like in these tests, we are trying to create disturbance, like maybe during Valsalva maneuver, from lying to standing, or during deep breathing. What happens is this set point is disturbed. So there are sensors, especially for blood pressure, you have baroreceptors, which sense this change and give feedback to the controllers in the brainstem. So there is a comparison between the set point and the altered variable. So the brain then gives output to its effectors. And the effectors in this case would be heart and blood vessels, both arteries and veins. So the signal goes to these effectors. The heart starts beating faster, pumping more. The blood vessels constrict. So the blood pressure is brought back to its normal state. That this is what a typical homeostatic control system works in a negative feedback manner. Now let's come on to our first test, deep breathing test. See, generally people think that even at rest, our heart rate is fixed, but that's not the case. Now, what happens is when a person is breathing in and breathing out, there is change in the heart rate. So that's what we are going to exploit during this deep breathing tests. So what is being done here is, you see, standard protocol has to be followed. As I mentioned in the beginning, the instructions are to be given to the subject. Generally, he should rest for 30 minutes, and then you start the test. You ask, and also, of course, you put on all the measuring things like, for example, ECG, beat-to-beat blood pressure. Then you also put in respiratory belt to measure respiration. And of course, it depends on your signals of interest. You can add so many, which I mentioned in the beginning. You can also pick up cardiac output conductance through, and then also pick up EDA and other signals, depending on your research interests. Now, what happens is the subject is asked to breathe in and out at a fixed rate. So there is a feedback given to the subject. There's a display on the monitor. So he has to synchronize with that. And also the technician gives him some hint, like breathe in and then breathe out. So in the end, whatever results you get, you try to find out the variation in the heart rate. So basically, it should be more than 10 to 15 beats per minute, the change between the highest and slowest rate. Then you also find out EI ratio, which is expiratory to inspiratory ratio. So you find out the longest RR interval in the ECG segment during expiration and divide it by shortest inspiratory RR interval for 5 cycle, average it. So generally EI ratio should be more than 1.2. And there are many factors which affect it. I have already mentioned most of them in the instruction. Now let's come on to the basis of this test. You see, I told you that the heart rate fluctuates during breathing. What is the reason for that? Now, what happens when a person inspires? So what happens in the chest? There is a negative pressure. So the more blood flows towards the chest. So the more blood flowing to the chest means more blood enters the right side of the heart. So in the right atrium, what happens? There is a stretch which results in brain bridge reflex. So there is a tachycardia. Then next thing is in the brain, when the inspiratory signals are generated, they irradiate from the respiratory center to vasomotor center. So there is a spill. So there is a direct stimulation of the vasomotor center. So there is increase in heart rate. That is the second factor. And the third factor is hearing Bruder reflex. So what happens when you inspire? So the chest inflates, the lungs inflate. So there is a little limitation of this factor. It depends how much is the expansion of the chest. But these stretched receptors, they give feedback to the brain centers, especially they inhibit the caudal ventrolateral medulla, which is a depressor center, and it results in tachycardia. And then baroreflex mechanism. So there are receptors located at the aortic arch and aortic sinus, which measure any change in pressure. So the feedback goes to the vasomotor center through the vagal centers, and then that's how they manipulate, as I mentioned also in my previous slide. And of course, there are other also minor receptors which are present in the ventricles and other areas which also contribute very minimally to this sinus arrhythmia. Now, this is about basis of deep breathing test. Now I'll hand over the presentation to my colleague Alex. Alex.
Thank you, Sanjay. All right, so for this part, I'm actually instrumented live to equipment. As you can see, I'm wearing a wireless module. This is the Bionomatics wireless module. I have a lead 2 configuration. So you can see here, I have electrodes here, and I have electrodes here. So I'm going across the chest. And I have a respiration belt. It's very important. This respiration belt is placed tight. So I would exhale, tighten the belt, and put it on, okay? This test can be performed with wired or wireless equipment. Right now, because I'm doing the webinar, I'm using the wireless version, and you can see it's very, very capable with managing any sort of movement-related artifacts. Okay, so now when the participant views this, it's key that they also can get some information about when to inhale, exhale, because they have to maintain 10 seconds for each respiratory cycle. So in Acknowledge, this is our software Acknowledge, which we use for recording, for visualization, and for data analysis. We can set up a gauge that the participant can see, and I'll follow this gauge now to make a few breaths according to the protocol, okay? And we'll see what happens. So I'm going to begin right now.
Up, up, up. The technician also keep giving the feedback to the subject.
Okay, we have a data set already recorded ahead of time, which we'll review for the actual data analysis. I will not record multiple cycles here, but I wanted to show you how we can present a nice interface to the participant for the duration of the recording. So what we're going to do next is we're going to show you how this is set up, and then we'll go and look into analyzing the data. So let's take our first poll right now.
Okay, here we go with the poll. All right, so how many years have you been conducting autonomic function testing for research for? We often have people who are just learning in our webinars, and we love having you here, but we also get experts as well who are just, you know, finding out what we've got going on. So I do have a question from the registration. Sanjay or Alex, I think either of you can answer this. So how is this used in psychiatric disorders like PTSD, mania, psychosis, and anxiety?
Yeah, that's a good question. In fact, it has a very good role in psychiatry, especially for prognosis. Of course, it's not very diagnostic, but most of these diseases, especially schizophrenia, post-traumatic stress syndrome, anxiety, depression, they're all associated with emotional factors and alteration of autonomic function testing. So this can be easily included both for clinical testing as well as for research autonomic function testing. So depending on the requirements, one can have wired and wireless solutions.
Okay, great. So I just closed the poll. Over half are just learning for the first time today, about a quarter, 1 to 3 years of experience, and then a smaller percentage in 4 to 6, 7 to 10 years, and actually 10%, 11 plus years doing this type of research. So Alex, before you jump in, there's a question that just came in by Paul. It said, where can you find this deep breathing gauge for subjects? Is that an Acknowledge, or did you bring that in from another place?
This is something that I'll explain right now.
Okay, great.
Yeah. Excellent. Okay, so we're on, right? Okay. Very good. First, I wanted to show you a screen capture of the experiment that was performed. So we recorded data from all these tests that we're going to present this week and next week. And because in Acknowledge, we can also synchronize with the video, with a camera, or even more than one camera if you have, we can now essentially watch a playback of the recording to see what happened. So we can see here the video, how the participants breathing in and out, and the gauge. Essentially, what we just saw done by me in real time. But here we also have a wired recording, and we recorded additional measures as well. We can see a blood pressure right here, and we can also see some additional electrodes, and I'll speak to that. Okay. So how is it done, right? How do we set it up? I mean, that's the question. So let's go and look inside the settings. So this was the recording, right? That we just did. There we go. Now, if we go to the setup channels in Acknowledge, I used a calculation channel, okay? And this calculation channel, and these, by the way, these templates, this data will provide, so you can essentially reproduce what we have done. Here we have a calculation channel that all it does is it provides a cosine waveform with a 10-second cycle, because we want the participant to produce a respiratory pattern that repeats every 10 seconds. That's the first step. We just need a signal that repeats every 10 seconds. And then in Acknowledge, we have this gauge that not everyone is aware of, but it's very useful. So we're going to click here, show gauge, and you can customize the gauge. So if we click on preferences, we can choose, first of all, we can choose what image to use. By default, we have a pressure, we have a stopwatch, and we also have a beats per minute display for heart rate. In this case, we have created our own image right here. You can just draw any image you want and save it with the correct dimensions, 451 by 451 pixels, and there you have it. That's step one. And the other thing you have to do is tell the software how to map the arrow that goes up and down to the image. Now, because here we have a sinusoidal waveform that goes from -1 to 1, we're simply telling the software, when you go from -1 to 1, the clockwise direction is going to be the inspiration, so that's going up, and the expiration is going to be the counterclockwise direction. So we're just mapping -1 to 0 and 1 to 360, and we're getting this movement. So that's really all that we're doing here. Okay. Now, one more thing. Here's the data now that we already collected, and it's very important that when you do these tests, you give time, 10, 15, 20 minutes for the person to relax before you actually do the tests. So I'm not going to use data recorded live, but I'll use the data we recorded ahead of time properly. So here we have this data. Now we'll go ahead and run through the analysis procedures here. Okay, so let me just okay. I'll minimize this window out of the way so we can see it a little bit better. Okay, in the software, in the Acknowledge software, we also have this this journal, okay, which you can turn on and off by there's a little control here, journal, you can turn it on and off, and the journal is very handy. You can put instructions in the journal. Okay, you put instructions in the journal for the person conducting the experiment and also for the person analyzing the data. So if it's for the lab technicians, you can put information here about a protocol, participant setup, and I've put in some information here about generally about the various measurements that you would need to connect the person to for AFT testing. And I've also have some information about practices. So you can really put anything you want in here. You just right click, manage PDFs, and you can add some PDFs to put information. So we have some instructions here that are used both during conducting the experiment and for the analysis. So let's look at the analysis. You may want to check whether the participant really was breathing at the correct rate. Okay, so this is our channel here that had the waveform that we created that showed the respiratory pattern. So we can overlay the channels, and you can see that the participant did very well. So sort of a sanity check to make sure everything's okay. And now we can proceed with the data analysis. We can do this data analysis using our scripts in Acknowledge. Okay, they can really speed it up, or you can do it manually. For the manual analysis, we've created video clips, which we'll share with you. Right now, I'll use a protocol relying on the scripts. So it's right here. So let's walk through this together. So with the respiration waveform selected, that's this one right here, we're gonna run the score respiration script. The scripts, I can use them from here, or I actually have created a toolbar with them. And these scripts are not a part of the software, but they will be provided as a part of the materials for the webinar. So you'll be able to access these scripts. Okay. So first, we're going to score the data here on the respiration. By highlighting each cycle that we want to analyze, we're having the software place markers at the points where we begin inspiration and the points where we begin expiration. Okay. I'm going to hide my my video so you can see the screen a little bit better. Okay. And every now and then I'll reveal the journal and hide the journal back. Okay. So let's hide the journal for a second. You can see here an icon where there's a nose pointing down. That means the air is coming out of the nose. That's the beginning of expiration. And then here we have inspiration, expiration, inspiration. So now we have performed this first step, which is to mark when we have inspiration and expiration. The next step, with the ECG, the electrocardiogram waveform selected, we'll run the script that will produce the heart rate and R2R interval channels. So we just click it, and now we have these new channels here. This channel gives us rate in beats per minute, and this channel gives us interval, RR interval, in seconds. This is essential. Now, the way we've created the journal, we've allowed for a place to paste the results of the analysis. So the first thing we're going to do is calculate the difference between the average accelerations and the average decelerations in heart rate. So for every respiratory cycle, you have a acceleration and deceleration of heart rate. We're going to average these and calculate the ratio using the script. So we just have to, with the rate waveform selected right here, we're going to place the I bar before the first respiration cycle and click HR difference. So it's going to paste the result right here. Okay, so the number is 23.455 beats per minute, which, as Sanjay said in the previous part of the presentation, is to be expected. It's high enough. The next part will calculate the EI ratio. Okay, so that's the expiratory-inspiratory ratio. For this, we have two different methods to calculate. one of the methods is simply to find the maximum over the minimum, okay? So that's simply taking the maximum duration R interval dividing by the shortest for the entire region, okay? And that's done by clicking the script EI ratio max. Okay, so that's our measurement. And then we can do also an averaging, okay? So we take the average of all the max and all the min, and then the ratio of that. So if we want to do that, we click EI ratio average. So here we have our measurements for all the tests that we wanted to perform. Very easy. But if you want to do this with students, then we have a manual procedure. So, you know, one by one, they can do the analysis so they understand exactly what is involved. When finished, you can save the journal in a variety of formats, Excel, for example, etc. And maybe you want to send these results. You can also print the journal, etc. All right. So at this point, I believe we can go to our next poll.
Great. I'll go ahead and launch the poll. Do you plan to perform this type of research for, or I guess autonomic function testing for research, teaching, or both? Okay, Alex. So I have a question about, you know, applications of this technology during exercise, especially heavy equipment. What do you think about that?
Heavy equipment, I guess we need to see exactly what is meant by that. But in general, for exercise, as you can see right now, I'm wearing sensors, wireless sensors, while moving around, and you can get very good results with mobile participants. Okay, blood pressure, however, you cannot be running around with a blood pressure measurement. So there's some limitations. We have a cardiac output module, which is wireless. So if you want to go completely free, you can also record cardiac output wirelessly. So the only consideration that you have to be think about as far as what's possible is for blood pressure. You want to keep the arm at constant height with respect to the heart, and for that you can wear it. You can wear a sling, for example. Okay, hope that helps.
Okay, yes, thank you very much. That was a great explanation. So now we're switching back to Sanjay, right?
Yeah.
Okay, so Sanjay, I'm making you presenter. And oh, by the way, over 50% of the people are using this technology for research, 12% teaching, almost a quarter both, and about 12% are just learning today. So thanks all for participating. Appreciate that.
And just to add a little bit to what just now Alex told about exercise, I request the attendee to go to the website, into the application section. You'll find many other applications as well about exercise. So let's go to the next test which we are going to perform today and demonstrate. It is Valsalva maneuver. You see, whenever a person strains, maybe for defecation, during coughing, what happens is the pressure in the thorax goes up. So once this pressure goes up, means the venous return is hampered. So as a result, there is variation in the cardiac output and also the heart rate. So that sets in a lot of cardiorespiratory changes in the subject. So again, as I told you in the beginning, so there is a negative control feedback mechanism which try to set in, and it controls the various variables within the normal setting point. Now, what happens in disease? It's not possible, so it's altered. That's what during research or during clinical testing, the doctor or the scientist try to find out. Now, as Alex told that for deep breathing test, the subject was given around 15 to 20 minute rest. Since it is a battery of test, and this is Ewing's battery we are following, so already the subject has rested for 15 to 20 minutes before deep breathing. So for Valsalva, when we switch from deep breathing to Valsalva, 5 to 6 minutes is more than enough rest. Now here, what is done is we clamp the nose, and then we connect the subject to a special pneumatic tube, which is also connected to a digital output on the screen, so that you know exactly how much is the pressure generated. So here the instruction is very important. The subject is asked to blow out from the chest and also using abdomen, and not from the mouth. So that instruction is very important. The subject holds the pressure at 40 millimeter of mercury, minimum 15 seconds. And then the clamp is released. And as Alex showed one picture of Slav, our colleague, he's wired. So you have ECG recording, you have NIBP, non-invasive, and also the respiratory tubing. And you can also add other signals if you're interested in some other parameters to be recorded during this maneuver. Now, this is repeated 3 times, and then either we pick up the mean or the highest value. So for Valsalva ratio, what is done is we, during the phase 4, which I'll explain in a minute, and there are 4 phases. So pick up the longest RR interval from phase 4 and the shortest from phase 2 and also 3, and then divide. That gives you some idea about the variability that is primarily because of parasympathetic tone. And then also we should, because as I told you, the ratio is reflecting parasympathetic activity. But at the same time, you can also record beat to beat blood pressure and then accordingly report it. Now, let me explain a little bit about the graph you get during this recording. So there are 3 channels recorded. The top one is blood pressure measurement, beat to beat. The second one is heart rate, and the third one is respiratory signals. So here at this point, the person is starting the procedure. So he started blowing out. So when you see here, when he starts blowing out, there is increase in blood pressure immediately and drop in heart rate. That happens because of the mechanical factor. So this is primarily because of the raised intrathoracic pressure, a little bit blood goes out into the circulation, which causes increased blood pressure, which is totally mechanical effect. And that also results in decrease in heart rate. Then what happens is, because the person is still blowing, there is no venous return, no blood coming back to the heart. So the output starts from the left side, the stroke output starts going down. So the initial part of phase 2, you'll see the blood pressure starts falling. And as a result, if you see, because of baroreflex mechanism, the heart rate starts increasing. Then the later part, you'll find because of the baroreflex mechanisms, they start operating. So they act on the heart, as I told you before. They also act on the vessels, the arteries and veins. So there will be increased sympathetic tone. So that will cause increased blood pressure, but it won't go high because the venous return is still little less. So when the nose is declamped, phase 3, so what happens is there is sudden drop of blood pressure again. You know what happens when the nose is declamped? The person stops breathing forcefully into the pneumatic tube. So because there is some vasodilatation in the pulmonary circulation, so there is less blood coming back to the left side. So the output decreases a little bit for a fraction of seconds. Then what happens? The person tries to now, because of negative feedback control systems in the phase 4, tries to regulate this variable. So the blood pressure starts going up. And of course, because the BP is going up, the heart rate, because of the baroreflex mechanism, going down. And then you'll find that the blood pressure overshoots the normal one, because you see this sympathetic output, is operating, and the peripheral vessels are already constricted. So what happens is this output, which is coming from the left side of the heart, is going into a vasoconstricted vessels, which raises the blood pressure a little higher. After another 1 minute or so, the blood pressure comes back to the normal state. And this is how we perform Valsalva maneuver. Now, my colleague Alex will demonstrate precisely and also show how the analysis is done. Thank you.
Okay, there we go, Alex.
Thank you, Sanjay. I've turned off my camera now so that you can see my full screen very nicely here. Okay, I will show you again a recording that we have performed for this. So just a few words to explain. Again, our participant is instrumented with a variety of sensors. We have electrocardiogram, we have respiration, blood pressure, we even have bioimpedance, etc., but we're not using them. And the participant can see this pressure gauge. Let's play back the recording here. So the participant can see this pressure gauge and the nose is clamped. So now they'll begin blowing into the tube connected to a pressure transducer. When that happens, they have to, there you go, you can see it happening. You can see also the pressure rising on the second channel, shows pressure. And they can also see the display here. So they look at the display, keeping it around 40 millimeters of mercury for 15 seconds, and then clamp is released. Okay, so that's basically what happens. And again, we are relying on the gauge display and the acknowledge software to make sure everything is very friendly for the participant. They can see what happens. Now, this is what the data set looks like when you perform this 3 times. And typically you perform the maneuver 3 times. You can already very quickly spot the typical pattern, which is just the same as the standard drawing of the response. Okay, before we go into data analysis, let's check once again what is required to make this work. Okay, first of all, if we go to media setup, you can record video and audio. You can choose your cameras. This is how we link the video to the audio. Okay, this is extremely handy because now that the video is linked, if we go to the playback viewer, we can see that the cursor is connected. So for example, I can place it right here. That's just as Swaf is getting ready to apply pressure. There we go. And then I can alternatively move the cursor here. Okay, go to the next step, the next test, and so forth. So this is very good to have this information afterwards when you're looking at the data. But the gauge is very important. Let's go to the gauge. Okay, this time we're using one of the standard gauges, simply a pressure gauge. The channel that's feeding into the gauge is the pressure channel. And this time the mapping is 1:1 because we want 1 millimeter of mercury to map to 1 millimeter of mercury. This measure with centimeters of water that was erroneously applied label. It's actually all in millimeters of mercury. Okay, so that's the step you need in order to provide the appropriate display to the participant. Now, once again, we'll bring up the journal. If you're not using the journal in the software, then you're really missing out on some of the capabilities of the software. It's very good for leaving notes. It's very good for writing down procedures. So here we have the Valsalva maneuver procedure. Here we have the analysis procedure, okay? So we can have these reminders. And even when we save this as a template, so save this as a graph template, which simply contains the settings, these instructions remain there, including all these other instructions that were embedded. Okay, let's follow the steps. This time I will not perform automated analysis. I want to show you in a little more detail some of the steps here. So here we have our electrocardiogram, and we can see here in the analysis procedure, the first thing we have to do is obtain the heart rate. So we go to analysis find rate, and we have a bunch of signal types here, and this is a human resting electrocardiogram. If they're exercising or something like that, we can increase the range. And the output can be rate beat per minute, but could be many other things. We're just going to keep it at rate beats per minute. Click OK, and now we have a new waveform called rate. That's the heart rate. I can rename it to HR if I want to. Next step is let's concentrate on one of the tests. For example, let's concentrate on this test, and I'll click here on the horizontal scale and change it. We're looking at 20 seconds division. This will give us a bit better view of the test, so I can clearly mark the different phases of the experiment. I'll use the focus areas in Acknowledge to do so. So here is, first of all, we're going to mark phase 1, which ends at where we see the end of this first stage of increase in the blood pressure signal. This is the focus area bar. Click on plus, and we have phase 1. Phase 2 ends right here, just before the mechanical release that takes place, like right here. And another way I can create a focus area, just right click, create focus area, and phase 2 is right here. The next phase, and if I want to zoom in to work a little bit more easily, I can just do so and look at like 10 seconds division. So this is the next phase. It's very short. The phase 3 is very short. That's this fall in blood pressure. So it's really just to about right here. So we'll go ahead and create phase 3. Okay, phase 3. And finally, we have phase 4. And phase 4 goes on from phase 3 up to the point where we see the end of the drop in heart rate. So this will be phase 4. So let's just type it in here, phase 4. Okay, now everything's clearly marked, and the next thing we want to do is calculate the Valsalva ratio. To calculate the Valsalva ratio, we want to take the highest heart rate during phase 2 and phase 3 divided by the slowest heart rate in phase 4. We can actually simply highlight all the data from here to here, phase 2 to phase 4, because the highest heart rate's always found in here, and the lowest heart rate's here. So I can just highlight it like this. We can even visually see it's right here is the highest, here is the lowest. And we set up measurement boxes in Acknowledge to give us the max of the currently selected channel, the heart rate, the minimum. Okay, so this would give us the minimum heart rate. So the maximum heart rate is 100.9 beats per minute. 54 beats per minute is the minimum. And we have a box here that calculates. What does it calculate? It calculates the first measurement divided by the second measurement. And it gives us 1.842. So we can just type in here for the answer 1.842. So that's the first step. Okay, so typically you want this result to be greater than 1.4. Now we can also perform baroreflex slope analysis on phase 4 in particular. So now we'll select phase 4 specifically. Okay, and first we want to low pass filter the blood pressure data. The raw blood pressure data is completely raw. So for the algorithm to perform optimally, you want to transform the data. So we'll go to digital filters, FIR, low pass, make sure we filter the entire waveform, and typically it's in a setting like this, you have to go to fixed 10 hertz. So it's a 10 hertz low pass filter. So variations in the blood pressure signal, there are higher frequency, essentially noise, will filter them out. Click OK, software will clean up the data significantly. Okay, so again, make sure phase 4 is selected, and then all we have to do is go to the analysis menu, hemodynamics, baroreflex slope analysis. The software will ask us to verify. It makes a guess which signals are ECG and blood pressure, so it's correct. So we just want to make sure it's correct. Click OK. And it's also going to ask us to select a representative cycle in the data. So I'll just grab one of these cycles. So, okay. And it will classify the blood pressure data. It will classify the electrocardiogram. You can see here on the bottom, QRS complex classified, star here for systolic, D for diastolic. And it provides the results for the baroreflex sensitivity. So we have 15.6 milliseconds per millimeter of mercury. We also get the R. Now, we can go to specific cycles in the data. Like if we think there's a problem with one of these, if it looks like an outlier, like none of them look like an outlier, but let's say like this one was an outlier, number 2, I could exclude it from the analysis and we'll recalculate. Of course, everything goes crazy then, right? Because it's not an outlier. So that's, and you can copy this. I can copy these measurements, close, and yeah, I'll just paste my results here. And at this point, we will have completed the analysis. Once again, I want to be clear about the equipment that's used for this kind of setup. So this is MP160. We have the NIBP module, which is just integrated, which is very small. And then you have all these smart amplifiers. This is the TSD 160D pressure transducer. So the tube, the pneumatic tube goes to that. And then these are some of the other options. And a bigger view of the connections, you know, blood pressure right here. It's measuring from the fingers. It is resting, as you can see, against a plate. So it's very important not to have stress on the arm. And this particular test was performed seated because it's a very minimum difference whether you do it seated or lying down. Okay, so blood pressure, cuff for calibration. We also were recording bioimpedance and electrodermal activity, but we're not analyzing them. We just have them for good measure. Okay, and this is another way in which you can have the arm in a cuff, and this is the physical connection to the pressure transducer. Let's take our next poll, and we'll continue with active standing and Sanjay.
All right, great info. So how do you currently measure blood pressure? Tell us that. We had Archana asked a question, is there a list in the journal of inclusion and exclusion criteria for subjects participating in Valsalva's? It might be unsafe, or it is unsafe in certain conditions like respiratory infections.
Yeah, definitely. You know, when we are doing these autonomic function tests, there are two components. One, you're doing research, the other one is clinical. So research generally we do on control subjects, which are normal healthy subjects. But in case of clinical setting, and also in case of controls, you need to be very careful of testing them before, you know, taking proper history before recruiting those subjects. So there has to be definitive inclusion and exclusion criteria. For example, if a patient is having syncopal attacks and the ratio is too wide, so then you can exclude the subject. And similarly, when you're doing head up tilt or lying to standing, you have to be very careful because it may precipitate syncope and other things. So that's, for especially research, clinical testing, you need to have inclusion and exclusion definitive criteria.
Okay, great. I just closed the poll, and about 24% of people are doing manual BP, 44% continuous non-invasive B2B, and several people have talked about wanting to add either manual or continuous non-invasive B2B blood pressure. Mostly they want to add the NIBP. So thank you all for participating, and back to you, Sanjay.
Yep, thank you. So now we will come to the last test in the battery, which is active standing, lying to standing. So one second. Can you see my slides, Brenda?
Yes, I can see your slides. It's the control variable blood pressure, change in the variable.
Yeah. So as I told you, most of these autonomic function tests exploit the normal negative feedback loop. So here what is being done is that we are disturbing the normal milieu by giving gravitational pooling of blood. So the subject is asked from a lying down position to stand, and then we record various parameters. So basically what's happening here is, as I told you previously, the blood pools in the periphery, in the blood vessels, in the lower extremities, and there is also, when the person is standing from lying, it's a kind of exercise of the lower muscles. So there is massive vasodilatation. So the blood stays in the periphery. So as a result, the venous return goes down. So once the venous return to the right side going down means there is less preload. So the output, stroke output also goes down. So as a result, the blood pressure starts falling when the person stands initially. So if you see carefully, one second, I'll go to the graph first and then explain. So if you see carefully, when the person stands, so what happens is that the heart rate goes up quickly. If you see the lower graph, so these are two tracing. The upper one is systolic and diastolic blood pressure. The lower one is heart rate. And in this rectangle, the area shows the person has already stood up, and these are cardiovascular responses we are noticing now. Now, if you see the lower graph, the heart rate suddenly increases when the person is standing. So basically, this is more of an exercise effect. Within 3 seconds of standing, the blood pressure, the heart rate and blood pressure increases mild. But then, as I told you, there will be stasis of blood in the periphery. So you see here, the blood pressure starts falling within 10 to 15 milliseconds. And then you see the heart rate, because it's falling, it will start increasing because of baroreflex mechanisms. And then later on, there will be correction, and the blood pressure will try to come back. It will normalize within 30 seconds. And how the test is done, you see again, as Alex told, the subject is wired, and 5 minutes of rest is enough if you're doing battery of tests. So he is already rested enough for deep breathing test and then also for Valsalva. So here you'll be recording ECG and blood pressure, and the subject is tied with these gadgets. So make sure that the arm, which is wired for blood pressure measurement, is at the level of the heart. Then, as I told you, that there is an immediate response and the blood pressure is corrected within 30 seconds, and there is what you call early stabilization. So in this case, the values we try to find out is 30-15 ratio. So we pick up after standing the 30th heartbeat and the 15th heartbeat and find out the RR interval, and this gives a 30-15 ratio, which is around 1.04. And of course, the other version for active standing is head up tilt. in between active standing and head up tilt, the head up tilt is missing the initial, counter regulation, because there is no pooling of there is pooling, but there is no return of the blood to the right side of the heart because of muscle pumping. And so we also find out the systolic and diastolic blood pressure fall. So in a normal person, the systolic should not fall more than 20 millimeter of mercury, and the diastolic blood pressure should not fall more than 10 millimeter of mercury. And the records, whatever records you get, you can further subject them to, like, for example, the baroreflex sensitivity, as Alex told you before, or you can also do heart rate variability in time domain or frequency domain. So I hand over for demonstration to Alex. Thank you.
All right, thank you. Okay, so once again, I'm keeping my camera off so you can see everything nicely, full screen here. Just like all the other recordings, we have also performed synchronized recordings. So here we can see how we're already at the stage where the participant is up. Okay, so always good to record the video. And now let's look at how we would analyze the data. In the interest of time, we are going to show some steps already are done, like the blood pressure is already scored because we already showed that. So we'll accelerate things a little bit. So how do we calculate the 30-15 ratio? That's the first thing we want to do. First, we need a waveform that gives us the R to R interval, and that's obtained with the find rate calculation that we just did from the ECG. So instead of getting beats per minute, we're getting R to R intervals. Okay, and you can see very clearly here the changes, right? And so we can also find acknowledge which peak we're currently on. Okay, that's given by an extra channel that I created, which gives us the peak count. Okay, so that's given by a measurement box. So we know where we are approximately, around peak 15 over here, around 25, 30. So if we highlight the data here, so like this, and we get the maximum R to R and the minimum R to R on channel 16, and then calculate the ratio, we get our number, 1.704. Again, to be very clear, all these analysis procedures will be shared as videos. So after the webinar, we will release short videos that explain analysis procedures in detail. Okay, but right now I want to show you what's possible. Okay, so the ratio here is 1.704, and you see these markers. This one says getting up. This one says standing. Now, these markers can be entered in real time or post acquisition. This is very important. If we come back to this recording, where, as you know, I'm connected to equipment right now. Okay, so here I am connected to equipment. If I just press the F1 key, there is a marker right here. F2, marker right here. This is very good for noting down interventions that are being made by the experimenter. So you can say, whenever we press the F1 key, it's going to mean that the person is standing up, and it's going to be in the global channel, and it's going to look like a flag. Okay, so now if I resume the recording and I press F1, we have a flag here, and the value is standing up. Okay, so that's something you can do when you're marking. But if you miss something, you can always add a marker later. You can just put it on here and type in something. Very important to know the capabilities of the markers. Okay. The next thing we want to do is look at the changes in systolic and diastolic blood pressure from baseline to adaptation. We've marked focus areas like we did for the previous one. So we have baseline, adaptation. Okay. So that's the adaptation stage is when the person is standing up. And we are looking on the systolic and diastolic channels. We're looking at the minimum blood pressure, so we can write it down here. So we have systolic is 125, diastolic is 93. And if we want to go and check our baseline, our baseline would be the mean, because we're just looking at the mean here. Okay, so the baseline was 157, so we went to 125, and the diastolic was just about the same. But keep in mind that the participant actually, it's a bit unusual because it has pretty high blood pressure, so maybe the results will be a little bit different than typical, but that's the way in which you would calculate it. These measurement boxes in the knowledge are very, very important and for calculating the results. Baroreflex sensitivity for the first 30 seconds of standing. We already showed how to calculate baroreflex sensitivity. We just highlight however long we want. So if we want 30 seconds, we can just go to delta T and see how much we're highlighting. So we can highlight 30 seconds, and then we run through the same analysis like before the baroreflex. So I will not do this again. But one thing I want to highlight is that we are also, for the duration of all these tests, and I'm going to hide by all the extra channels here, all these tests, we are also recording bioimpedance, cycle by cycle. We're also recording electrodermal activity. We're not doing anything with the electrodermal activity right now, but we are doing something, and we can do very useful operations because we have the continuous signal for bioimpedance. So Acknowledge can ensemble average the bioimpedance readings for specific beats. So I have placed markers here over the beats that I want to average. So this is my baseline, and this is the stage where we have this adaptation when the person has just stood up. So to show you here the results, we have the baseline measurements, and the software can calculate in this measurement box here, calculates the stroke volume, 99 milliliters, and for the adaptation stage, 70 milliliters. So that's to be expected. When you're standing up suddenly after lying, the stroke volume is expected to go down, and we are able to pinpoint this, and because we have this capability beat by beat to measure continuously the bioimpedance, and then by selecting specific beats, we can also avoid beats that are a bit noisier. Okay. Not only this, we're also looking at the cardiac output by multiplying the stroke volume by the heart rate. So cardiac output, while during the baseline is about 6.3 liters, and when the person's standing up, it's around 6.6 liters. So not very different, but of course the stroke volume is what changes. There are many more things we want to show you, of course, but right now I'm going to switch over back to Sanjay because we just have a few last parts. I believe we have a poll before that, if not.
Yes, we do have a poll, so go ahead and launch it.
Yeah.
This is our third poll, I think, to look here. Are you planning to set up an autonomic function testing lab? Tell us what's going on with you. And then when you set it up, you should let us know. We'd be happy to let publish information about your work in our newsletter. That might be a fun thing to share with our customers. All right, so hi Swapan, I see you asked a question. Have these tests been applied in research settings such as yogic breathing maneuvers? And I can tell you that I looked up real quick some citations, and there's 168 citations for BioPAC and yogic. I don't know how to say that word, but any other comments, Sanjay, about this?
Yeah, it's a perfect solution for investigating yoga and yogic postures, because you have both wired and wireless solution, and there is a logger also. So almost all these variables can be recorded wirelessly. So it's a perfect solution for doing studying yoga and yogic exercises.
Okay, great.
And
Well,
before switching to Sanjay, can I just show one more image and then we switch over?
Yeah, please.
Yep, there you go. Just close the poll, and a lot of people interested in setting up a lab. Some people are maybe, and some people are no. So I guess they're just here to learn for fun.
Yep.
Yeah.
Very good. Well, I just wanted to show for bioimpedance, you can see how we're using these paired electrodes, right, in these pictures. It's very important so you can keep the distance fixed. Okay, so we're using this on both sides of the body. I just wanted to make this very clear, right? And then just physically, what it looks like when you're laying out these various modules on the table. I mean, they're tiny. These are the various modules. Okay, so very small amplifiers that we're looking at, and once again, that for the teaching equivalence for this exists for the teaching system. And now let me go back to Sanjay.
Okay, I'm making Sanjay the presenter. There you go.
Yeah. Thank you, Brenda. So we are almost at the last phase of our webinar 1. So we'll be doing the second webinar on 12th, where we'll be talking about hand grip test, cold pressure test, and mental arithmetic test. Now, just to complete the story, I have also listed what other tests can be done because of limitation of time. And some of the tests were very simple and straightforward, no technology involved. So no recording special techniques involved, only the analysis part. So we skipped them, like for example, heart rate variability and others. But that can be easily done using acknowledged software, to be very clear. Now, regarding the sweat test, as I told you, sudomotor sweat test. So one of the tests is known as QSAR test. It is quantitative sudomotor axon reflex test. It measures the peripheral post-ganglionic sympathetic cholinergic system. So here we have special capsules which are attached to the 4 parts of the lower limbs and upper limbs. And then the capsule is very special. It has a compartment for delivering inotrophoritically acetylcholine, and then there is another compartment which picks up any moisture, and then it gives you the results. So it's a very good technique to nail any peripheral neuropathies. So as I told you that it's a battery of tests. So we combined all kind of tests, especially in clinical setting, to pin the diagnosis, whether the neuropathy is central or peripheral, which nerves are involved. The other test is thermoregulatory sweat test. This is more of a global test. You need a specialized sweat chamber, and you need a special dye, which is sprayed all over to the subject, and then the temperature in the sweat chamber is raised, and then there will be a color change once sweating take place. So that gives you, clear-cut, very objective picture of the subject, which areas are sweating and which areas are not sweating. So you can link it with the other tests and also the clinical history and also clinical examination and reach at a diagnosis. The other one is electrodermal activity. I request the participants to go online. There are many webinars on this. So basically, electrodermal activity measure, the number of active sweat glands. So it's very easy to employ. Alex also showed in one of his experiments that it's employable, very easy test, and it gives you a lot of information. Then, of course, as I told you during active standing, head-up tilt is done using a motorized tilt table, and all the recordings are done. So it is more done for clinical studies, and for teaching and basic research. Lying to standing, active standing is more than enough. It gives you enough information about the baroreflex sensitivity. And baroreflex sensitivity, Alex already demonstrated to you precisely in Valsalva maneuver. It can be employed, and Acknowledge is a very powerful tool which has inbuilt software to do this. Just press the button and you get the results. Heart rate variability, as I told you in the beginning, the heart rate varies with the different rhythms. Maybe it's baroreflex, or it's sinus rhythm, or it's circadian rhythm, it's thermoregulation. Many factors are there. So we have in Acknowledge software, there is a special analysis of heart rate variability, which you can do either time domain, or you can also do frequency domain analysis for heart rate variability. Then, of course, another very objective method is microneurography. So either you pick up the sympathetic nerve activity from the muscles or the skin, and you can link with the other tests, battery of tests, or with the history, and pin the diagnosis. Precisely, you know where is the peripheral neuropathy. And then, of course, you have biochemical analysis of these noradrenaline, or you can also do spillover tests by, radio labeled noradrenaline. And then you can also do MIBG scan. Again, it's a labeled chemical, so this gives you some idea. So, but these are not very commonly employed, and both in research and clinical setting. And the last one is known as TRAV. It is transradial electrical bioimpedance velocimetry. So it is available with BioPack. You can go to the application web page and you'll find the whole details. Basically, what's happening here is we are putting 4 electrodes, and the recording is very simple and straightforward. It's very handy. It's not like measuring the thoracic bioimpedance for cardiac output. So what is done here is the rhythmic fluctuation of the cardiac outputs are picked up by TRAV, and then you can find out both stroke volume, cardiac output, and also the peripheral resistance. And it is a very valid, time tested, and for research it's being used very commonly. So anyone who is interested can either contact the local suppliers or can also go online and see further details. So this is in brief about the various tests which are done. We'll meet again on 12th to complete the story. We'll cover other autonomic function tests. So now I can hand over to Brenda for further.
All right, great. We did complete the rest of our polls, so we'll just move right into the Q&A. So let's just turn your video on for me, Sanjay, during the Q&A, and then we'll take our first question. So actually, this was from a while ago. Any recommendation for doing Valsalva or deep breathing while prone in the MRI?
Yeah. So as I told you in the beginning, that most of the equipments we sell are all MRI compatible. I think Alex,
just a quick clarification. There are MRI versions and non-MRI versions, right?
Yeah.
So, but all the signals pretty much are also available in MRI versions.
Yeah. It's very robust,
And so, especially in connection to Valsalva, because you just need to maintain this pressure, right? And so the tube can be can go all the way from the equipment inside, so from the control room inside the chamber. It's just a pneumatic line, and in Acknowledge, the screen where we show the gauge, you can have it go on a separate monitor screen, for example, and then this way the participant can see it. So really, you can definitely do that. Most importantly, we also have blood pressure for the MRI, a machine for blood pressure for the MRI. We can do cardiac output in the MRI. We have bioimpedance, electrocardiogram, respiration. So all the signals that you would need for AFT testing, autonomic function testing, you can do it in the MRI.
Okay, great. Well, thank you. All right, so I'm going to go back to the top of the list. There's still a ton of people on. So, and if you're raising your hand, I do see that we have a hand raised. Please just add your question to the GoToWebinar control panel, and I'll read it off. Okay, so Grant asked, can autonomic function testing be accomplished with bioimpedance pre-ejection period measures alone, or is it based on having continuous BP measures?
I guess it depends what sort of measurements you're after, right? I mean, you can choose only a subset of the measurements. Of course, you have less information then. It's not typical to skip blood pressure for a lot of these tests. Blood pressure is sort of central to the tests.
Okay.
I mean,
great. Okay, so then Anita said she missed how you calculate stroke volume with the sensors. I don't know if that's something you want to cover after.
Yes, so for the stroke volume, we'll have a separate clip we'll post because we only had a limited amount of time, and this particular calculation has to be explained very clearly. In fact, we are planning at some point to do a webinar specifically on the topics of bioimpedance, but this calculation we'll address via just a separate video clip we'll put on our channel.
Okay, and I think you answered this, is the system analyze blood pressure variability?
For blood pressure, I guess it, like depends what is being asked, but we have specific blood pressure analysis routines in Acknowledge. So if you already have our software, you can check the capabilities of the blood pressure analysis. So, and if it's something a bit different, just let us know. We can explain how to do it.
Okay. Yeah, there's a lot of questions. So I'm going to just take this last two questions here. And let's see, Stefan is asking, does the Acknowledge program work with the MP36 student modules? No, it doesn't. You can use the MP36R.
Even though it doesn't, you can open the files in Acknowledge. Okay, so the data analysis can take place in Acknowledge. That's fine. So if you have data recorded from a teaching system, you can use our research software to analyze.
Okay, and Danilo is asking, what tube amplifier do you need for the Valsalva to measure pressure?
For pressure.
There's two different definitions of pressure, right? So you have the pressure where you're maintaining a pressure, okay? In this case, you have the DA100C amplifier. I'll try to grab one from over here, see if I can bring it in front of the camera. Okay, so this is the DA100C amplifier, okay? And then this pressure transducer is the wrong model. You want the TSD160D. And then you have a pneumatic line, okay? So a pneumatic line from the front. The camera is trying to focus on me instead of on the amplifier, but DA100C amplifier, TSD160D, even though it says A over here, I'm using this for something else. The range of the actual transducers is different. And then for the blood pressure, then you're using the NIBP 100E, which is the integrated unit, or the D, which is the standalone blood pressure system. They function identically. The E has the advantage that it just snaps onto the rest of the modules, and it's smaller. It's completely integrated into Acknowledge. The D is the typical unit you'd see in a hospital setting. They function equivalently, but that's standalone unit, and you just feed the signals into the red. So either way.
Okay, well, thank you all. Thank you, Alex and Sanjay, so much. You've done an awesome job on this webinar explaining everything. So thank you for all the work that you did. I know I did get some feedback from some of the attendees saying that they were grateful and that the presentation was really, really good. So thank you for all of your work. I do have some closing comments that I want to share. It's been an hour and a half, I just realized, so this was perhaps our longest webinar that we've had. So we do offer live webinars every month, usually almost every month, and then we have a lot of them. We've been doing them for 5 years, so there's a lot of webinars here. You can go watch any of these webinars just by clicking on the form and then like submitting the form, and then it'll give you access to the pre-recorded version. Since there's a lot of technical information here, I wanted to share that we do have a support team, an awesome support team that provides support to you over email, over phone. You can just email them email them at support@biopack.com, or call us, or you can submit a support request. And I just wanted to share that our next webinar is May 12th. It's part 2 of the autonomic function testing, and we'll cover the isometric hand grip test, cold pressure. I know Swaphan was asking about that. Swaphan was a presenter at another webinar of ours a year and a half ago, so it was fun seeing him on here. And also we'll cover mental arithmetic. So you can watch our on-demand webinars anytime. You can, hopefully we'll see you next week as well. We'll have Sanjay again and our CEO, Fraser Finlay. Okay, so I just want to remind everyone that today's webinar was recorded. We'll email you a link of the recording, the slides, and the Q&A document. When you close the GoToWebinar window, you'll see a survey. Please complete that so we have your feedback and ideas for future webinars. And finally, of course, you can visit biopack.com for additional references, including screencasts, videos, application notes with step-by-step instructions, and information about upcoming events, including in-person events. We've gone back to in-person events, and actually Alex will be at one next week, or is that tomorrow that you're starting? You're starting your
flying out tomorrow. Yeah.
So that's why he's not going to be on the webinar next week. He'll be at an in-person event in London, ISMRM. So, all right, Alex, Sanjay, anything else before we conclude?
Maybe switch the screen to my screen just for a second.
Sure. All right, there you go.
I just wanted to show you that, you know, I've been connected now for about 4 hours, by the way, and we still have absolutely excellent data quality. So for long-term experiments, the bionomatics is really a very good way to go. This is like as real settings as it gets during a webinar. If you want to check it's real, it's real.
Good one, Alex. And just to add, participants must have seen that recording AFT is very tedious and time consuming, and it needs a lot of precision and experience. So my word of advice to the beginners would be that one must follow all the guidelines, and especially preparation of the subjects, instruction of the subjects, because in that way you'll be able to have a reproducible data in the end. Thank you.
All right, I'm just going to grab a screen grab of this live data collection, so hang on.
The battery life is really good.
Right,
the battery life of this module, when it's connected like it is right now, it's 3 days, 72 hours. So you can, in the lab, you can follow for a very long time.
And plus, even the logger has around 24 hours battery life.
Yes, the logger is 24 hours. Yeah.
That's good.
Okay, well, awesome job, everyone. Thank you again. Thank you, attendees, for
Thank you, Brenda. Thank you, Alex. Bye-bye.
All right, take care, everyone.
Thank you, Brenda.
Today's webinar. Bye.